Initial values of storage element circuits with switches. At this point, in your academic career, you've encountered differential equations that require initial conditions. And a lot of times you'll see me write them as ICs. Question. What is an initial condition? From your mathematics course, you most likely heard that initial conditions refer to values given for a function at the initial at the initial starting point. In plain language, it just means what's happening at the starting point. On the other hand, the differential equation describes what happens after t equal to 0. In other words, it's 0 plus. In summary, the condition for first order equations, the condition for second order equations, there's conditions are typically specified as input values. To help determine the behavior / characteristics of the function. Because that initial condition then changes the constants that are the solutions to the differential equation. This language must be translated into circuit language. To give context, what exactly the initial conditions do. So we now concentrate on finding the change in the storage element variables. What are the variables? It's going to be the voltage and the current when the switch is thrown. And so when we say when it's thrown, it's going to be either open or closed, of course. The throwing of a switch occurs instantaneously. That can drastically affect some variables while others will not change. So again, we have the same language that we've already talked about with switches. We talk about t equal to 0 minus, t equal to 0 plus. So this means here, we need to compare for a capacitor, we need to compare VC at 0 minus versus VC of 0 plus and IC of 0 minus versus IC of 0 plus. And for inductors, we do the exact same thing. We're going to compare IL of 0 minus to IL of 0 plus and VL of 0 minus versus VL at 0 plus. So we now look at those variables here. Okay, we're now going to look at those variables. So what we're going to find here is that I'm going to start with capacitors and then I'll go on to inductors. So now we're going to be looking at the initial values of capacitors with switches. So let's go do that. So we're going to look at the behavior of the capacitor at t equal to 0. And we'll start with the voltage. And so if I start looking at that, we're going to talk about the capacitor's voltage. So let's look at that. So what do we know about the capacitor? The process of depositing charge onto the plates takes time. So one way we can actually look at this thing here is that physically, it makes sense that as incoming charge sees the charges already on the plate. Therefore, there is an electrical repulsion to the incoming charge. In other words, if I have a plate and then I have my wire here, what I'm going to see here is that there is charge already built up on the plate. So if I have charges that are coming in, these charges on the plate are applying some electrical repulsive force. So because of this, these incoming charges, we would then say that these incoming charges feel a kind of, let me move this down, kind of electrical repulsion. Or not repulsion, but electrical resistance. Now, of course, this isn't resistance, but in picture-wise, this is what you should be thinking in your mind here. So now, so what we're seeing here is that this tells us that capacitors do not allow charge to instantly fully charge a capacitor. In reverse, it takes time to pull charges off the plate or plates as well. Therefore, the moment a switch is thrown, at this infinitesimal moment in time, the voltage across the capacitor cannot change instantly. So that tells us then that the voltage of the capacitor before has to be equal to the voltage right when the switch is thrown. In other words, capacitors voltage cannot change instantaneously. Mathematically, how does this play out? We know the capacitor equation tells us that the current of the capacitor is, of course, the derivative of the capacitor voltage with respect to time. So we can approximate this as dVc delta t. So if I look at it this way, if the voltage was to change instantaneously, the capacitor's current would have to be infinite. One can show this because if it changes instantly, that means that delta t has to go to 0. So then if I look at this, if I have a limit of delta t approaching 0, that change happens instantaneously. Then I look at d delta v delta t, and that clearly goes to infinity, which then implies that the current of the capacitor must also approach infinity. Well, clearly that's hogwash. Clearly, an infinite current is not physically possible, and the voltage cannot change instantaneously. This implies then that then delta VC of delta T must be finite. The fact that IC of T must be finite prevents VC of T from changing instantaneously. This means, again, the capacitor voltage cannot change instantly. So picture-wise, what does that mean? So let's imagine, so suppose one has a discharging capacitor. So if I was to plot this, what do I actually see? What I see here is that if I have a charge on a capacitor, this is telling me that this is VC of 0 minus. So at VC of 0 minus, we have this capacitor that's coming in. Now a switch is thrown. When this switch is thrown, this capacitor can then discharge to a different value. So then this would be VC of 0, this would be VC of T. But at this point right here, when we look at this, that tells me that at this point, we have that VC of 0 minus must be VC of 0 plus. That voltage cannot change instantaneously. So now let's go to the capacitor's current. The capacitor equation clearly restricts how the voltage cannot change instantly. However, there is no such restriction on the current changing instantly. And the change of DIC dt can be instantaneous. There's no restrictions. This implies a possibility that there are discontinuities in the current. So in other words, IC of 0 minus in general, in fact, the majority of the time, are not the same once the switch is thrown. So then we say that the capacitor's current can change instantly. So picture-wise, it is very possible to have an instantaneous jump. So if I look at what I'm seeing here, you could imagine that we have a switch that hasn't been thrown, and this would be the current of the capacitor at 0 minus. Now, at t equal to 0, a switch is thrown. So what you're going to see here is that I could have a discontinuity in the jump here. So if I'm looking at this, let's say that this is IC of t, and then what will happen here is that the current of the capacitor will have this discontinuity, and then it's going to approach, typically, it will go back to 0 as it reaches its steady state here. So what you're seeing here is that right here at this point, this would then be IC of t, that's what the curve would be. But if you look at this point right here, what you're seeing here is that there are 2 points that you got to look at. You got to look at this guy, and you have to look at that guy right there. You could clearly see that IC of 0 minus is clearly not equal to that right there. And that's because right here, we see that there's an instantaneous jump. So in summary, That tells us that the voltage of the capacitor cannot change instantly, but the current of the capacitor most likely will change instantaneously.